What if, at this very moment, there's another version of you living a completely different life in another universe? Picture this somewhere out there. A twin of you might be making choices you never did, following paths you never took, all because reality isn't as singular as we once thought. This isn't science fiction, it's a real possibility that some of the brightest minds in physics are taking seriously. The idea of parallel universes, once confined to the pages of comic books and late-night debates, has now crept into the halls of cutting-edge science, and the evidence is more compelling than you might think. Imagine a cosmic kaleidoscope where every twist creates a new version of reality, a multiverse where infinite possibilities unfold simultaneously. It sounds like something straight out of a dream, but scientists have uncovered clues that suggest our universe might just be one thread in a vast, tangled web of existence. From the eerie behavior of quantum particles to the mind-bending math of string theory, there are startling reasons experts believe we're not alone in the grand scheme of things. And today, we're diving deep into 25 of the most fascinating pieces of evidence that could prove parallel universes aren't just fantasy, they might be science. Why does this matter? Because if true, it changes everything. The idea that there are countless versions of reality means the cosmos is far stranger, far grander than we ever dared to imagine. It challenges our very understanding of existence, pushing the boundaries of what we think is possible. So whether you're a skeptic or a believer, buckle up, we're about to embark on a journey through some of the most electrifying ideas in modern science. By the end, you might just find yourself looking at the night sky and wondering who else is out there. At the heart of this staggering idea lies quantum mechanics, a realm where particles behave in ways that defy common sense. Take the famous Schrödinger's cat thought experiment, where a feline trapped in a box is both alive and dead simultaneously until someone observes it. This paradox reveals a bizarre truth. At the quantum level, particles exist in multiple states at once, a phenomenon called superposition. But what happens to all those possibilities once observation collapses them into a single outcome? In 1957, physicist Hugh Everett proposed a radical answer: they don't disappear. Instead, every possible outcome plays out, but in separate, newly formed universes. Picture a tree with infinite branches sprouting every time a quantum event occurs. In one reality, the cat lives. In another, it doesn't. In one universe, you turned left on your way home today. In another, you went right, setting off an entirely different chain of events. This is the many worlds interpretation, and it suggests our reality is just one thread in an ever-expanding tapestry of parallel existences. What makes this more than wild speculation? The math holds up. Quantum equations don't account for possibilities vanishing, they simply branch. While critics argue these other worlds are untestable, supporters point to quantum experiments where particles seem to remember their superposition, as if echoing choices made in alternate realities. Whether or not we ever prove these hidden worlds exist, the many worlds interpretation forces us to confront a humbling possibility. Every decision, every chance event might be writing infinite stories across the cosmos. The universe didn't just expand after the Big Bang, it exploded outward faster than the speed of light in a fraction of a second, a phenomenon called cosmic inflation. This wasn't a gentle unfurling, it was a violent stretching of space itself, leaving behind ripples in the fabric of reality. And those ripples might hold the key to proving we're not alone in the cosmic scheme of things. In 2014, scientists working with the BICEP telescope at the South Pole thought they'd struck gold. They detected faint swirls in the cosmic microwave background, the afterglow of the Big Bang, that seemed to match predictions of gravitational waves from inflation. While those initial results were later found to be dust interference, the hunt didn't end there. Updated data and more advanced instruments like the BICEP array have kept the possibility alive, suggesting inflation didn't just happen, it left fingerprints. But here's where things get wild. If inflation occurred once, what's stopping it from happening again and again? Think of it like a pot of boiling water where bubbles constantly form and expand. Each bubble could be a self-contained universe with its own unique physics, sprouting endlessly in an infinite cosmic foam. Some might have stronger gravity, others might have light that travels slower or faster than ours. This bubble universes theory, championed by physicists like Andre Lind, implies our entire observable cosmos could be just one tiny pocket in a multiverse where the laws of nature aren't universal at all, but local. The math behind inflation doesn't just allow for this scenario, it practically demands it. Once inflation starts, according to quantum field theory, there's no clean-off switch. It keeps happening in patches, birthing new universes indefinitely. If true, it means every possible variation of physical constants exists somewhere out there. A universe where stars burn colder, another where time flows backward, even one where you made every possible choice in every possible combination. Critics argue this is untestable speculation, but supporters counter that the very existence of our finely tuned universe where constants like gravity and electromagnetism are perfectly balanced for life makes more sense if there are infinite versions where those values shuffle randomly. We just happen to be in the one where the dice rolled in our favor. So the next time you gaze up at the night sky, remember, what you're seeing might not be the whole story. It could be just one page in an endless cosmic library, each book telling a different tale of reality. String theory, the ambitious framework aiming to unify all forces of nature, paints a picture of reality so vast it makes our observable universe feel like a speck of dust. At its core, the theory suggests that the fundamental particles we know aren't dots at all, they're tiny, vibrating strings. But here's the catch: for the math to work, these strings need to dance through not just the 3 dimensions we experience, but a mind-boggling 10 or more. That's where things get really strange. Hidden within those extra dimensions are intricate shapes called Calabi-Yau manifolds complex, twisted geometries that dictate how strings vibrate. Think of them like the hidden machinery behind reality's curtain. Each unique configuration of these shapes changes how strings move, which in turn alters the laws of physics in that universe. And according to calculations by luminaries like physicist Brian Greene, there aren't just a handful of possible configurations, there are 10 to the power of 500. That's a 1 followed by 500 zeros, a number so colossal it dwarfs the atoms in our observable universe. What does this mean? If every possible Calabi-Yau shape exists somewhere, then each one corresponds to a universe with its own distinct physics. Some might have gravity 1,000 times stronger, rendering stars unstable. Others might lack electromagnetism, preventing atoms from ever forming. Our universe, with its precise balance of forces, could simply be one lucky roll of the dice in an endless cosmic casino. This sprawling landscape of possibilities isn't just a quirk of string theory, it's an unavoidable consequence. The math doesn't point to a single, tidy solution. It screams for a multiverse. Critics argue this makes string theory untestable, but supporters counter that it's the only framework that elegantly merges quantum mechanics and gravity. And if the math insists on 10 to the power of 500 solutions, who are we to argue that only one gets to exist? After all, nature rarely favors simplicity when complexity is on the table. So the next time you hear someone dismiss parallel universes as fantasy, remember, the equations scribbled in physics labs might already be describing them. Consider the extraordinary precision of our universe's settings, like a cosmic lock where every tumbler must align perfectly for life to exist. The force of gravity, the strength of electromagnetism, even the density of dark energy, each is balanced on a razor's edge. Alter any one of these constants by a fraction and stars wouldn't form, atoms would fly apart, or the universe would collapse in on itself. It's as if the dials of reality were set with meticulous care, a phenomenon physicists call the fine-tuning problem. This precision stretches credibility. The cosmological constant, which drives the universe's expansion, is fine-tuned to 1 part in 10 to the power of 120. To put that in perspective, it's like throwing a dart blindfolded across the Milky Way and hitting a bullseye the size of a single atom. The odds are so astronomically low that scientists grapple with a haunting question. Is this staggering improbability just a cosmic fluke or evidence of something deeper? Enter the Goldilocks principle. Like the porridge in the fairy tale, our universe isn't too hot or too cold. It's just right for life. But why? One compelling answer lies in the multiverse. If infinite universes exist, each with randomly dialed constants, it's no surprise that at least one landed in the sweet spot. We're not special. We're simply the beneficiaries of a cosmic lottery where trillions of other universes might be barren, their physics hostile to anything resembling life. Critics argue this is a cop-out, a way to avoid confronting the eerie perfection of our cosmos. But proponents counter with the anthropic principle. We can only observe a universe capable of producing observers. It's like a fish marveling at how perfectly water fits its needs, not realizing other environments might exist where it couldn't survive. The multiverse offers a framework where fine-tuning isn't a mystery but an inevitability. Imagine a vast cosmic library where each book contains a different set of physical laws. Most are gibberish, their pages filled with equations that lead nowhere. But somewhere in that infinite stack, there's a volume where the numbers align, and that's the one we're reading from. Whether you find this idea unsettling or exhilarating, one thing's clear. The fine-tuning problem doesn't just hint at parallel universes, it practically demands them. In 2008, astronomers analyzing data from NAS, a Wilkinson microwave anisotropy probe, stumbled upon something bizarre: hundreds of galaxy clusters hurtling through space in the same direction at staggering speeds, as if tugged by an invisible hand. They called it dark flow, a cosmic mystery that defies everything we know about the universe's structure. These clusters weren't just moving randomly. They were racing toward a specific point beyond the edge of our observable cosmos, a place where no known mass or energy should exist. The implications sent shockwaves through astrophysics. Gravity's reach isn't infinite, its influence diminishes with distance. So what could possibly be pulling entire clusters millions of light years away? One daring explanation whispers of neighboring universes. Picture our universe as a soap bubble floating in a frothy sea of others, each with its own physics. If another bubble universe drifted close enough, its gravity might subtly tug on matter in ours, creating this unexplained flow. It's like standing in a forest and feeling a breeze from a clearing you can't see. The trees block your view, but the wind tells you something's out there. Skeptics argue it could be a statistical fluke or an artifact of measurement, but the data refuses to fade. Later observations from the Planck satellite and X-ray telescopes found hints of the same phenomenon, deepening the puzzle. If dark flow is real, and that's still a big if, it could be the first tangible clue that we're not floating alone in the multiverse foam. Think of it this way: the cosmic microwave background, the afterglow of the Big Bang, is like a snapshot of the infant universe. But dark flow suggests something outside that picture is warping it, like an unseen magnet bending iron filings. The most thrilling possibility: we might be detecting the gravitational shadow of another reality brushing against ours. Until we have better tools, it remains a tantalizing maybe, but in science, maybe is where the most thrilling discoveries begin. Black holes have long been the ultimate cosmic vaults, places where matter, light, and even information itself seem to vanish forever. But what if nothing truly disappears? Stephen Hawking's groundbreaking work revealed that black holes aren't completely black. They emit faint radiation, slowly leaking energy until they evaporate entirely. This phenomenon, now called Hawking radiation, solved one mystery while creating another. if a black hole vanishes, what happens to all the information it swallowed? According to quantum mechanics, information can't be destroyed. It has to go somewhere. That's where things get surreal. Physicist Leonard Susskind proposed a jaw-dropping solution. The information isn't lost. It's encoded on the black hole's event horizon like a cosmic hard drive, preserved in a two-dimensional hologram. This holographic principle suggests our three-dimensional reality might be a projection of data stored at the universe's edges. But there's another twist. Some theories speculate that when a black hole evaporates, the information doesn't just linger. It might get funneled into a brand new universe, a baby universe budding off from our own like a hidden branch on a tree. Imagine tossing a book into a black hole. From our perspective, it's gone. But in reality, its information could be etched onto the event horizon's surface and later reborn in a fledgling reality with entirely different physical laws. This idea dovetails with wilder hypotheses about white holes, the theoretical opposites of black holes. While black holes suck everything in, white holes could spew matter and energy out, possibly into another universe. It's as if black holes aren't just cosmic trash compactors, they're portals recycling information into new realms we can't see. Skeptics argue this is speculative, but the math holds tantalizing clues. If black holes can spawn new universes, it would mean our own universe might have been born this way, a cosmic Russian nesting doll with layers of reality we're only beginning to fathom. Whether these ideas hold up or not, one thing's certain. The black hole information paradox doesn't just challenge our understanding of space and time. It cracks open a doorway to the multiverse, suggesting that every black hole might be a creator, not just a destroyer. Here's a chilling thought. What if you're not the product of billions of years of evolution, but a fleeting accident, a momentary flicker of awareness conjured from the random jostling of particles? That's the unsettling premise of Boltzmann Brains, a thought experiment that pushes the limits of probability and reality itself. In the late 19th century, physicist Ludwig Boltzmann proposed a radical idea that the universe's apparent order might just be a statistical fluke. Given enough time, even total chaos could, by sheer chance, arrange itself into something structured. Fast forward to today, and cosmologists have taken this idea to its extreme. In a universe that lasts forever, random quantum fluctuations could theoretically assemble a fully formed, self-aware mind, a Boltzmann brain out of the void. These phantom observers would pop into existence, experience a brief moment of consciousness, then vanish, utterly convinced they'd lived a full life in a real world. Statistically speaking, these freak accidents should vastly outnumber ordinary, evolved beings like us. After all, assembling a single brain by accident is far more probable than crafting an entire universe hospitable to life. So why don't we find ourselves as these disembodied minds? The answer might lie in the multiverse. If countless universes exist, each with different conditions, then evolved consciousness becomes inevitable somewhere in the cosmic sprawl. Suddenly, the odds tilt. Real beings in stable universes outnumber the fleeting Boltzmann hallucinations. It's like comparing a single random lightning strike to a thriving city illuminated by countless electric lights. One might dazzle for an instant, but the other represents enduring reality. Critics argue this is philosophical sleight of hand, but supporters counter that the multiverse offers the simplest escape from the Boltzmann paradox. Without it, we're left with a disturbing conclusion that we're far more likely to be momentary illusions than enduring inhabitants of a real cosmos. The multiverse doesn't just explain why we exist, it explains why we're here to wonder about it at all. So next time you question your own reality, take comfort. You're probably not a Boltzmann brain, but the very fact that we can debate it hints at something extraordinary. The cosmos might be vast enough to make sense of even the most improbable truths. Ever wonder if reality is just an ultra-advanced video game running on some cosmic computer? The simulation hypothesis, first seriously proposed by philosopher Nick Bostrom, suggests that at least one of three staggering possibilities must be true. Either civilizations like ours almost always go extinct before reaching technological maturity, they choose not to create realistic simulations, or we're almost certainly living in one. But here's where it gets wild. What if those simulations aren't running in isolation? What if every possible simulation exists simultaneously, creating a multiverse of virtual realities nested inside an unfathomable cosmic mainframe? Bostrom's trilemma forces us to confront an uncomfortable truth. If advanced civilizations ever develop the power to simulate conscious beings, the number of simulated minds would dwarf biological ones. Statistically, the odds tilt heavily toward us being artificial constructs in someone else's experiment. But why stop at one simulation? Quantum mechanics offers a tantalizing clue. At the subatomic level, particles exist in fuzzy, undefined states until measured, almost like a computer rendering details only when observed to save processing power. This quantum indeterminacy could be the cosmic equivalent of lag, a system prioritizing resources by only fully resolving realities when they're being watched. Think of it like a vast multiplayer game where unobserved zones remain low resolution to conserve energy. Now scale that up infinitely. Each time a quantum event forks reality, Schrödinger's cat being alive or dead, for instance, it might represent the simulation spawning new instances to explore all outcomes. String theorist Brian Greene once quipped that the multiverse could be nature's way of avoiding buffering, with every possibility pre-rendered in parallel universes to prevent computational overload. Skeptics argue this is just modern metaphysics dressed in tech jargon, but the math has eerie resonance. If our universe operates with finite Planck lengths and speeds, a pixelated, frame-limited reality, it aligns unsettlingly well with the constraints of information processing. Even the infamous measurement problem in quantum mechanics, where observation collapses probability waves into definite states, mirrors how video games only generate graphics when a player looks at them. So where does that leave us? Either we're living in a lone simulation, an ancestor simulation run by future humans, or we're one thread in an immeasurable digital tapestry where every possible universe is being computed somewhere. Both options bend the mind, but the second opens a dizzying prospect. Perhaps the multiverse isn't just a feature of physics, but the inevitable architecture of a reality too complex to run any other way. Picture a loaf of raisin bread baking in an oven that never turns off, forever expanding, endlessly rising, with new raisins constantly forming as the dough stretches into infinity. That's the essence of eternal inflation, a theory pioneered by physicist Alan Guth that takes cosmic inflation and cranks it up to 11. Unlike the standard Big Bang narrative, where inflation was a brief burst that jump-started our universe, eternal inflation suggests the process never actually stops. Instead, it keeps happening in pockets, birthing new universes like bubbles in a never-ending cosmic foam. Here's how it works. Space-time isn't expanding uniformly like a balloon inflating. It's more like a fractal where certain regions keep stretching exponentially while others slow down and pinch off into stable universes, our own being one of those lucky bubbles. The inflationary field, a kind of energy that drives this expansion, behaves like a hill with valleys. Most of the time, it rolls downhill, releasing energy that fuels the rapid stretching of space. But quantum fluctuations can kick it back up the hill in certain areas, causing those regions to keep inflating while the rest settle into stable universes. The result, an infinite tree of budding realities, each with its own unique physics, forever branching off from an ever-growing trunk of space-time. What makes this more than just a pretty metaphor? The math behind inflation doesn't have a built-in stop mechanism. Once it starts, quantum effects ensure it keeps going somewhere. even if individual universes like ours freeze into their own stable configurations. It's like a wildfire that can't be fully extinguished even if you stamp it out in one place. Embers keep flaring up elsewhere, igniting new blazes. This means our entire observable cosmos could be a single bubble in an infinite multiverse, with countless others growing beyond our horizon, forever out of reach. The implications are staggering. If eternal inflation is real, then every possible combination of physical constants exists somewhere in this fractal sprawl. Universes where gravity crushes stars into black holes before planets can form. Others where dark energy rips atoms apart before life ever gets a chance. And maybe, just maybe, a handful where the numbers align perfectly like ours, to allow galaxies, planets, and curious minds to ponder their own existence. Critics argue this is untestable, but supporters point to subtle clues. The cosmic microwave background's temperature fluctuations, for instance, might carry echoes of quantum jitters from our bubble's violent birth. And if we ever detect gravitational waves from the earliest moments of inflation, their patterns could reveal whether our universe was truly a lone event or just one flicker in an eternal firestorm of creation. So the next time you look up at the night sky, remember, what you're seeing might not just be a vast universe. It could be a single pixel in an infinite cosmic screenshot, one frame in a film that never stops rolling. And somewhere out there, in the endless froth of eternally inflating space, another version of you might be gazing up at their own sky, wondering the exact same thing. Dark matter has long been the universe's most frustrating ghost, elusive, invisible, yet making up 85% of all the matter in existence. We feel its gravitational pull on galaxies, watch its effects on cosmic structures, but it refuses to interact with light or ordinary matter in any way we can detect. What if the answer isn't some exotic particle, but something far stranger? What if dark matter is just us, or rather, a shadowy twin of our own matter, lurking in a parallel universe so close yet so far? This is the spine-tingling premise of mirror matter theory. Imagine a universe identical to ours in every way, same particles, same forces, but flipped like a reflection in a cosmic mirror. In this mirrored realm, protons might carry negative charge instead of positive, and left-handed particles become right-handed. The two realities could coexist, separated only by an extra dimension too small for us to perceive. Normally, these twin worlds would never interact, their particles oblivious to one another. But gravity, unlike other forces, might leak across dimensional barriers, allowing mirror matter to tug on our universe without ever being seen. Here's where it gets wild. If mirror matter exists, it wouldn't just explain dark matter. It could rewrite the rules of reality. Collisions between ordinary and mirror particles would be vanishingly rare, but not impossible. Some physicists speculate that certain unexplained events in particle detectors, like the mysterious ghost hits observed in dark matter experiments, could be mirror particles brushing against ours for a fleeting instant before vanishing back into their hidden dimension. Even more mind-bending, if mirror stars and galaxies exist, their light would be invisible to us, but their gravity would sculpt the cosmos just like dark matter does today. Critics argue this is speculative, but the math holds surprising promise. Mirror matter neatly sidesteps the thorniest dark matter puzzles, like why we've never directly detected it despite decades of searching. If it's literally matter from another universe, of course it wouldn't behave like anything in our particle zoo. And if gravity is the only bridge between worlds, it explains why we only sense dark matter's gravitational whispers, not its electromagnetic shouts. Think of it like two cities built on opposite sides of a sheer cliff. Residents in one can't see or hear the other, but if someone drops a rock off the edge, both sides feel the vibration. Mirror matter could be the unseen city, its existence revealed only by the tremors it sends through space-time. Whether this theory holds up or not, one thing's certain: the idea that dark matter might be ordinary matter in a stranger form forces us to rethink not just the cosmos, but what else might be hiding in the shadows just beyond our reach. Einstein famously called it spooky action at a distance, the bizarre phenomenon where two quantum particles become entangled, instantly influencing each other no matter how far apart they are. Defying the speed of light, this connection appears to transmit information faster than physics should allow. Einstein hated the idea, dismissing it as impossible. But what if the particles aren't communicating across space at all? What if they're linked through something even stranger, parallel universes? This mind-bending twist comes from physicist David Deutsch, who proposed that quantum entanglement isn't about particles talking to each other in our reality. Instead, they're interacting with versions of themselves in alternate universes. Picture two coins flipped simultaneously in different realities. In one world, both land heads. In another, both land tails. From our perspective, it looks like the coins are magically synced, but in truth, their outcomes were always coordinated across parallel timelines. This could explain why measuring one entangled particle instantly chooses the state of its partner. The decision was already made, just not in our universe. The double-slit experiment offers eerie support for this idea. When particles like electrons are fired through two slits, they create an interference pattern, as if each particle passes through both slits simultaneously, like a wave. But if you try to observe which slit the particle takes, the interference vanishes. The particle suddenly acts like a single, well-behaved object. Deutsch argues this isn't just quantum weirdness, it's evidence of parallel worlds subtly interfering with ours. The interference pattern emerges because countless versions of the particle are taking different paths in alternate realities, their combined influence creating the wave-like effect. The moment you observe it, you force one outcome to lock in for your universe, but somewhere else, another version of you witnesses the opposite result. Skeptics dismiss this as philosophical sleight of hand, but the math holds up. Unlike traditional interpretations of quantum mechanics, which struggle to explain why observation collapses probabilities, the multiverse view offers a clean solution: nothing collapses. Every possibility plays out just in different branches of reality. What we perceive as randomness might be the shadow of infinite versions of ourselves making every possible choice. Think of it like ripples overlapping in a pond. What looks like chaos from above is actually the sum of countless individual waves. Quantum entanglement could be the same, not spooky action at a distance, but the quiet hum of parallel worlds brushing against ours. Whether this interpretation survives future tests or not, one thing's certain: Einstein's spookiness has become a doorway to something far grander, a multiverse where every quantum flicker tells a story we're only beginning to decode. What if the Big Bang wasn't the beginning, but just the latest chapter in an endless cosmic cycle? Nobel laureate Roger Penrose's radical theory of conformal cyclic cosmology dares to suggest exactly that. Picture a universe where time isn't a straight line but an infinite loop, where the death of one cosmos seeds the birth of another in an eternal dance of destruction and rebirth. At the heart of this idea lies a paradox. As our universe expands toward heat death, a cold, empty void where even black holes have evaporated, it also stretches space-time so thin that distances and durations lose all meaning. Penrose realized that in this state of ultimate dilution, the universe effectively resets. The vast, lifeless expanse of the far future becomes mathematically identical to the hot, dense singularity of the Big Bang. It's like crumpling a piece of paper into a tiny ball. No matter how complex its creases at the smallest scale, it's just a smooth point again. But here's where it gets wild. Each new cycle isn't an identical copy of the last. Subtle imprints carry over through Hawking points, glowing remnants of ancient black holes from previous universes, now embedded in the cosmic microwave background like fingerprints from a forgotten age. Penrose and colleagues claim to have spotted these eerie hotspots in satellite data, patches where temperatures spike in perfect concentric circles. If true, they'd be cosmic gravestones, evidence of supermassive black holes that once ruled a universe long gone. Imagine throwing a stone into a pond. The ripples fade, the water stills, but at the quantum level, faint vibrations linger. In Penrose's model, our universe is that pond, and Hawking points are the last whispers of energy so immense they echo across eternity. Each new Big Bang inherits these subtle asymmetries, meaning no two cycles are exactly alike. One universe might birth more black holes, another might tweak the strength of gravity just enough to allow life in forms we can't fathom. Skeptics argue these temperature anomalies could be statistical noise, but Penrose counters that their geometric precision defies random chance, even more provocative. If cyclic cosmology is real, then everything we see, every galaxy, every law of physics might just be one variation in an infinite series. The atoms in your body could be recycled stardust from countless previous universes, rearranged in endless configurations across eons we can barely comprehend. This isn't reincarnation, it's reality itself rebooting, each iteration writing its own unique code. Whether the evidence ultimately supports it or not, Penrose's vision forces us to confront a humbling thought. We might not be living in the universe. We might be living in a universe, one page in a cosmic book where the story never ends. It just starts over again and again, with infinite variations on the theme of existence. The idea that our three-dimensional universe might just be a holographic projection from a two-dimensional surface sounds like science fiction, but some of the sharpest minds in physics are seriously considering it. This isn't about futuristic tech or virtual reality headsets. It's a radical rethinking of space-time itself, born from the study of black holes and quantum gravity. And if true, it could mean everything we perceive, stars, planets, even our own bodies, are just shadows cast from information encoded on the cosmic equivalent of a flat screen. It all started with a paradox. When matter falls into a black hole, it seemingly vanishes forever, violating quantum mechanics' ironclad rule that information can never be destroyed. But in the 1990s, physicist Leonard Susskind and others proposed a solution. The information isn't lost. Instead, it gets smeared across the black hole's event horizon like data etched onto a cosmic hard drive. Even wilder, the three-dimensional stuff inside the black hole might just be a projection of that two-dimensional data, a hologram. Extend this idea to the entire universe, and you get the holographic principle. Our 3D reality could be a rendering from information stored at the universe's boundary, like a movie playing on the inner surface of a sphere. Think of it like a credit card hologram. Tilt it, and a 3D image seems to float above the flat surface. Now imagine that on a cosmic scale, except instead of a tiny sticker, the surface is the edge of the observable universe, and the image is everything within it. This isn't just metaphor, the math checks out. Quantum field theory equations work just as well in 2 dimensions as in 3, suggesting our extra dimension might be emergent, not fundamental. But here's where parallel universes creep in. If our universe is a hologram, what's stopping others from being projected from their own unique boundaries? Picture multiple holograms floating in a higher dimensional space, each with its own screen encoding a separate reality. Some might have slightly altered physics, a tweak in the quantum code here, a glitch in gravity there. Others could be vastly different, with extra forces or dimensions we can't begin to fathom. Support comes from an unexpected place, the cosmic microwave background. Scientists analyzing its patterns found anomalies that align with holographic noise, subtle pixelation in the fabric of reality. It's as if we're seeing the graininess of the universe's underlying code, hints that space-time might have a finite resolution, like a digital image blown up too far. Critics argue this is speculative, but supporters counter that holography solves thorny problems. It neatly unites quantum mechanics and relativity, 2 frameworks that otherwise refuse to play nice. And if the universe really is information at its core, then multiple files could exist in the cosmic database, each a self-contained reality, rendered from its own unique data set. So the next time you reach out to touch something solid, ask yourself, are you feeling an object or just the echo of information whispered from the edge of existence? The holographic principle doesn't just challenge our place in the cosmos, it suggests we might be living in a universe more fragile and more extraordinary than we ever dreamed. What if reality as we know it isn't a vast, three-dimensional expanse but a thin, shimmering sheet, drifting like a leaf in an unseen cosmic ocean? This is the mind-bending premise of brain cosmology, a theory that reimagines our universe as a membrane, or brain for short, floating in a higher dimensional space called the bulk. And if that's true, the cosmos might be far more crowded than we ever imagined, with other brains hovering just out of reach, each hosting its own alternate reality. Imagine a loaf of bread where each slice represents a separate universe. Normally, these slices never touch, but what if they could? In the ekpyrotic theory, developed by physicists Paul Steinhardt and Neil Turok, our Big Bang wasn't the beginning of everything. Instead, it was the explosive aftermath of two brains colliding in the bulk, releasing enough energy to birth an entire cosmos. Think of it like slamming two sheets of paper together. The moment of impact creates heat, light, and ripples that set the stage for galaxies, stars, and eventually us. But here's the twist: these collisions might not be one-time events. If brains oscillate through the bulk, they could collide again and again, each crash triggering a new cosmic cycle. It's as if the universe has a reset button, with every collision wiping the slate clean and starting fresh. This challenges the traditional Big Bang narrative, offering an alternative where time stretches infinitely in both directions. No singular beginning, no definitive end. Evidence for this idea remains elusive, but tantalizing clues exist. If brains brushed against each other in the past, the gravitational waves from those encounters could leave faint imprints in the cosmic microwave background, subtle ripples in the afterglow of creation. Some researchers argue that certain anomalies in the microwave data, like unexpected cold spots or unusual polarization patterns, might be fingerprints of these ancient brain collisions. What's even wilder, if other brains exist nearby in the bulk, their gravity could subtly influence ours. Picture two ships sailing side by side on a calm sea. Even if they never touch, their wakes can interfere, creating ripples that betray each other's presence. Similarly, unexplained gravitational tugs on distant galaxies or the mysterious alignment of cosmic structures might hint at unseen brains lurking just beyond our perception. Critics dismiss this as speculative, but proponents argue it solves long-standing puzzles. For one, it sidesteps the need for a singular, infinitely dense Big Bang singularity, a concept that still baffles physicists. Instead, the ekpyrotic model offers a smoother, cyclic vision of cosmic history, where energy is recycled rather than conjured from nothing. And if true, it means our universe isn't floating in isolation. It's part of a bustling higher dimensional neighborhood where other realities might be closer than we think, separated not by light years but by dimensions we can't yet fathom. So the next time you gaze at the night sky, consider this. What looks like empty space might be anything but beyond the stars, beyond the galaxies, beyond even the edges of our observable universe. There could be entire other worlds floating, drifting, waiting for the moment their path crosses ours again. And when it does, the cosmos might just hit reset, starting the story all over. Time flows forward like an unbreakable rule. Eggs crack but never uncrack, ice melts but never reforms spontaneously. This one-way street, called the arrow of time, is driven by entropy, the universe's tendency toward disorder. But what if that's just a local quirk? What if elsewhere time runs in reverse, with shattered glasses leaping back onto tables and smoke pooling into unburned logs? The idea isn't as far-fetched as it sounds, and it might explain one of physics' deepest mysteries. At the heart of this puzzle lies CPT symmetry, a fundamental principle stating that if you flip a particle's charge, mirror its position, and reverse time, the laws of physics should hold perfectly. And for isolated particles, they do. But when you zoom out to cosmic scales, time stubbornly marches forward. Why the asymmetry? Nobel laureate Roger Penrose and physicist Lee Smolin have proposed a radical fix. Maybe it's not asymmetric at all. If our universe is just one bubble in an infinite multiverse, other bubbles could have arrows of time pointing in the opposite direction, perfectly balancing the cosmic books. Enter the Janus cosmological model, named after the two-faced Roman god. This theory suggests the Big Bang birthed not one universe, but two mirror images racing away in opposite temporal directions. From our perspective, the other universe would appear to be rewinding, its inhabitants perceiving us as the ones living backward. It's like standing back to back with someone. Your forward is their backward, yet neither is objectively correct. Support for this comes from quantum weirdness. At microscopic scales, particles don't care about time's arrow equations work just as well run backward. Some interpretations suggest our perception of time emerges from quantum decoherence, where trillions of particles agree on a direction. But in a mirror universe, that consensus could flip, creating an equally valid reality where causality runs in reverse. Critics argue we'd never detect such a universe, but anomalies lurk. Certain particle interactions show slight asymmetries that, in a Janus-style cosmos, could be echoes of our twins' inverted timeline. And if entropy isn't fundamental, just a statistical trend, then a universe where it decreases would be just as lawful as ours, merely rare from our vantage point. Picture a Möbius strip where up and down depend on your position. Time's arrow might be similarly relative, a cosmic illusion forged by our limited perspective. If true, the multiverse isn't just a collection of alternate histories, it's a kaleidoscope of temporal directions, where every possible flow of time plays out somewhere. The next time you watch steam rise from your coffee, consider this. Somewhere in a universe unseen, that steam might be doing the exact opposite, swirling back into the cup as time itself flows the other way. One of quantum mechanics' most perplexing mysteries lies in a simple act, looking at something. At the subatomic level, particles exist in fuzzy, undefined states until measured. Then, like a ghost snapping into solid form, they choose a definite position or spin. This observer effect has haunted physicists for decades. Why should reality care whether we're watching? A radical answer comes from the von Neumann-Wigner interpretation. Consciousness itself might be the force that collapses quantum possibilities into concrete reality. Think of it like a cosmic choose-your-own-adventure book. Every quantum event an electron's path, a photon's polarization, presents multiple outcomes. But when a conscious mind observes it, the story branches, not because of detectors or lab equipment, but because awareness acts as a pruning shear, snipping away unrealized paths. In this view, the universe isn't a pre-written script. It's a sprawling, undecided draft until a conscious observer, whether a scientist or a curious house cat, forces it to commit. The implications are staggering. If consciousness shapes reality, then the multiverse isn't just a collection of parallel worlds, it's a garden where minds cultivate their own unique versions of existence. Each observation could be a fork in the road, with one outcome crystallizing in our universe while others bloom elsewhere. This might explain why quantum particles seem to know when they're being watched. They're not reacting to machines, but to the presence of awareness itself. Critics dismiss this as borderline mysticism, but the math has eerie resonance. Quantum equations don't specify what constitutes an observer, leaving the door open for consciousness to play a role. Even wilder, some experiments with delayed choice measurements suggest particles can retroactively decide their behavior based on future observations, as if time itself bends to accommodate conscious choices. Picture a vast, shimmering quantum ocean where every ripple represents a possible reality. Most fade harmlessly, but when a conscious mind dips in, one ripple solidifies into a wave, while the rest continues spreading in unseen dimensions. Whether this interpretation holds or not, it forces us to confront a dizzying possibility. We might not just be inhabitants of the multiverse, we might be its architects, shaping reality one observation at a time. Our universe might be sitting on a cosmic time bomb, one that could rewrite the laws of physics in an instant. It's called false vacuum decay, and it hinges on a terrifying possibility. The vacuum of space might not be as empty or as stable as we think. Right now, the universe exists in what scientists call a metastable state, like a ball resting in a shallow valley. It seems stable, but give it enough energy, and it could roll into a much deeper valley, rewriting reality itself. Here's the nightmare scenario. Quantum fields permeate the universe, dictating everything from particle masses to the strength of gravity. These fields exist at their lowest energy states, or so we thought. But if there's an even lower energy state lurking out there, our universe could suddenly drop into it like a trapdoor opening beneath our feet. The moment this decay begins, a sphere of true vacuum would expand at the speed of light, overwriting the laws of physics as it goes. Atoms would dissolve, forces would unravel, and the very fabric of space-time would reconfigure into something unrecognizable. But there's a bizarre silver lining. In an infinite cosmos, some regions might escape this wave of annihilation. Picture a wildfire sweeping across a continent. A few islands, by sheer chance, remain untouched. These isolated pockets would become their own self-contained universes, frozen in the old physics while the rest of reality transforms around them. Over time, each pocket might develop its own unique laws, sprouting new cosmic bubbles with entirely different rules. It's like shattering a mirror and finding that every shard reflects a different version of reality. The scariest part, we wouldn't see it coming. The collapse would move at light speed, giving no warning. One moment, everything's normal. The next, an invisible wall of doom wipes out existence as we know it. And yet, perversely, this could already have happened elsewhere in the multiverse. Entire universes might have blinked out of existence, their final moments erased from cosmic history, while new ones emerge from the wreckage with physics we can't even imagine. Is this just doomsday speculation? Surprisingly, no. Particle accelerators have searched for signs of vacuum instability, and while they've found nothing yet, the math doesn't rule it out. In fact, the Higgs field, the same one that gives particles mass, appears to be precariously balanced, existing in a state that's stable for now, but not necessarily forever. Some calculations suggest that in trillions of years, quantum fluctuations could trigger this decay spontaneously. But here's the twist: if other universes have already undergone false vacuum decay, their survivors might be thriving in realities where gravity is stronger, light is slower, or entirely new forces exist. Our universe, then, could be one of those lucky remnants, a bubble that escaped an ancient cosmic reset. Whether this is a ticking time bomb or a hidden engine of multiverse creation, one thing's certain: the ground beneath our feet and the stars above our heads might be far less permanent than they seem. Deep in the cosmic microwave background, the faint afterglow of the Big Bang lies an anomaly so vast it defies explanation. Stretching nearly 2 billion light-years across, this eerie, cold spot registers significantly cooler than its surroundings, as if the universe itself has a cosmic bruise. Physicist Laura Mersini-Horton proposed a startling explanation. It might be the scar left behind when our universe collided with another in the multiverse's tangled web. The cold spot isn't just a minor temperature dip. Statistical analyses show its odds of forming randomly are about 1 in 50, unlikely enough to raise eyebrows. Traditional explanations, like a vast cosmic void, fall short. Empty regions of space should cool light passing through them, but not to this degree. Mersini-Houghton's alternative: imagine two soap bubbles brushing against each other in a sink. Where they touch, energy is transferred, leaving a subtle distortion. If our universe grazed another during inflation, the gravitational tug of war could have stretched space-time in that region, leaving behind a chill in the cosmic microwave background, a ghostly handshake from a parallel reality. Support for this idea comes from quantum predictions. Mersini-Houghton's models suggested certain large-scale patterns should appear in the universe's structure if inflation occurred alongside other universes. When the Planck satellite mapped the cosmic microwave background, it found anomalies, including the cold spot that aligned eerily with her predictions. It's as if the cosmos whispered back, confirming a shadowy neighbor we can't yet see. Critics argue the cold spot could still be a fluke, but the implications are hard to ignore. If true, this marks our first potential evidence of a multiverse, not just as theoretical math, but as a physical imprint on our sky. Future telescopes, like the European Space Agency's next-generation cosmic observatories, could scrutinize the cold spot for secondary signatures, like polarized light patterns unique to brain collisions. Until then, this cosmic bruise remains a tantalizing hint that we're not alone in the grand expanse. Just one bubble in a froth of countless others, some close enough to have left their mark. So the next time you hear static on an old TV, remember, a fraction of that noise is the echo of creation itself, and hidden in its patterns might be the fingerprints of realities beyond our own, waiting for us to decipher their secrets. Numbers are everywhere, governing the orbits of planets, the spirals of galaxies, even the beating of your heart. But what if math isn't just a tool we use to describe reality? What if it is reality? That's the bold claim at the heart of Max Tegmark's mathematical universe hypothesis, a theory so radical it suggests every possible equation, every geometric shape, every abstract structure that can exist in math must exist physically somewhere in the multiverse. Tegmark's idea slices the multiverse into 4 levels, with level Roman 4 being the most mind-bending. Level I is simply distant regions of our own universe beyond the cosmic horizon. Level Roman 2 introduces bubble universes born from eternal inflation. Level Roman 3 brings in the quantum many worlds branching, but level Roman 4, it obliterates the line between math and existence entirely. Here, universes aren't just governed by mathematical laws, they are mathematical objects. A donut-shaped universe real, a cosmos where time has 5 dimensions. Exists a reality built entirely on fractal equations. Somewhere, it's out there. This isn't just philosophical musing. Math has an uncanny ability to predict physical phenomena we've never observed, like Dirac's equations foreshadowing antimatter or Einstein's relativity hinting at black holes long before we found them. Tegmark argues this isn't coincidence. It's evidence that math isn't merely a human invention, it's the fundamental fabric of existence. Think of it like a library. Most multiverse theories suggest the library contains every possible physical book variations on our universe's theme. Tegmark's level Roman 4 says the library also contains every possible abstract book stories written in languages we can't speak, geometries we can't visualize. In one book, gravity operates inversely. In another, circles have corners. These aren't metaphors, they're alternate universes as real as ours, just built on different mathematical blueprints. Critics call this mathematical platonism gone wild, but the hypothesis dodges a thorny question. Why this particular math? If our universe runs on quantum fields and relativity, why not another set of rules? Level Roman 4 answer is elegantly ruthless, no preference. All mathematical structures exist equally, and we simply inhabit one self-consistent slice. It's the ultimate democracy of realities. No universe is special, just differently computed. The implications are staggering. It means every time a mathematician scribbles an equation, they might be drafting the laws of a hidden cosmos, that unsolved theorem on your professor's chalkboard. It could be the gravitational constant of a universe where black holes sing. Even dreams, those chaotic neural firings, might echo the physics of a distant mathematical realm bleeding into our perception. Whether Tegmark's vision holds or not, it forces a profound shift in perspective. The cosmos might not be a machine. It might be a mosaic, an infinite tapestry of truths where every possible pattern, no matter how alien, finds its place in the grand computation of existence. So the next time you solve for X, remember, you're not just crunching numbers, you might be touching another reality. What if death itself was an illusion, not just metaphorically, but physically? The quantum suicide thought experiment takes Schrödinger's cat to a chilling extreme, proposing that in an infinite multiverse, consciousness might be tethered to timelines where survival is guaranteed, no matter how improbable. Picture a scenario where a researcher straps themselves into a diabolical machine linked to a quantum event, say, a radioactive atom with a 50% chance of decaying within 1 minute. If the atom decays, the machine activates, ending the experiment and the researcher's life. But if it doesn't decay, the timer resets and the test continues. According to the many worlds interpretation, both outcomes happen. In one branch, the researcher dies. In another, they survive. Now here's the twist. From the researcher's subjective perspective, they can only experience the branches where they're alive. Every time the quantum trigger fires, their consciousness splits, but they're only aware of the reality where the gun doesn't go off. After 1,000 iterations, statistically, they should be dead. Yet from their viewpoint, they'd have miraculously survived 1,000 near-certain deaths, like flipping a coin and getting heads every single time. This apparent immortality isn't magic. It's the brutal math of parallel realities filtering experience through the sieve of survival. The implications rattle our understanding of fate. If consciousness navigates solely through timelines where it persists, then improbable events, narrow escapes, freak survivals, might not be luck at all, but inevitabilities in a multiverse where every possible outcome plays out somewhere. A skydiver whose parachute fails might find themselves in a branch where it spontaneously deploys at the last second. A cancer patient could experience remission against all odds while other versions of them succumb. The observer's perception becomes a cosmic selection bias, where only the winning universes get witnessed. Critics argue this reduces to solipsism, a universe that bends to preserve individual awareness, but proponents counter that it's simply probability playing out across infinite canvases. There's no supernatural intervention, just the cold calculus of branching realities. The surviving researcher isn't special. They're one thread in a tapestry where countless others meet grisly ends. Their continued existence feels miraculous only because the alternative branches are, by definition, unobservable to them. This thought experiment forces a haunting question. Are we here because the universe is fine-tuned for life, or because we're the versions of ourselves who can ask the question? The quantum suicide paradox doesn't just challenge our notions of mortality. It suggests that in the multiverse's infinite sprawl, death might be less an endpoint and more a road we simply never walk down. Neutrinos are the universe's ultimate ghost particles, so elusive they can pass through light years of lead without a single interaction. But these phantoms have a bizarre quirk. They shapeshift as they travel, flipping between 3 known flavors, electron, muon, and tau neutrinos, in a phenomenon called neutrino oscillations. For decades, physicists assumed this was just quantum weirdness at work. But what if these flavor flips aren't just random dances? What if they're glimpses of something far stranger, a hidden handshake between our universe and others? The puzzle deepens with sterile neutrinos, hypothetical particles that don't interact with any known force except gravity. Unlike their ordinary cousins, these shadowy variants could slip through dimensions we can't perceive, acting as cosmic messengers between parallel realities. Imagine a hallway with invisible doors. Each time a neutrino oscillates, it might briefly step into another dimension, exchanging properties with its counterpart in a neighboring universe before snapping back into ours. This isn't pure speculation. Equations modeling sterile neutrinos require extra dimensions to balance, hinting at a multiverse lurking beneath the math. Support comes from anomalies in neutrino experiments. When scientists tally up expected neutrino counts versus what they detect, there's often a mismatch, a deficit nicknamed the reactor antineutrino anomaly. Sterile neutrinos could explain these gaps, but only if they're vanishing into dimensions beyond our own. Even stranger, some detectors pick up unexpected oscillation patterns at specific energy levels, as if neutrinos are resonating with hidden physics. It's like tuning a radio and catching static from a station broadcasting in another reality. Critics argue these anomalies could be calibration errors, but proponents point to projects like the upcoming Deep Underground Neutrino experiment, designed to hunt for sterile neutrinos with unprecedented precision. If they exist, their gravitational whispers might nudge neutrinos in ways that defy three-dimensional logic. Picture throwing a ball in a closed room. If it occasionally veers off course, you might suspect a hidden draft. Neutrino oscillations could be our draft, betraying the presence of unseen universes brushing against ours. The implications are staggering. If sterile neutrinos truly bridge dimensions, every oscillation is a cosmic handshake, a fleeting connection to realities with different physical laws. Somewhere, a neutrino's twin might be absorbing our universe's weak nuclear force, while another leaks dark matter into ours. It's a two-way street, with particles acting as diplomats between worlds. So the next time a neutrino detector blips, remember, that signal might not just be from deep space. It could be a postcard from a parallel cosmos, sent via dimensions we're only beginning to suspect. Black holes were already the universe's most enigmatic prisons until physicists stumbled upon a paradox so severe it threatened to unravel quantum mechanics itself. The AMP's firewall paradox, named after its discoverers Olmary, Marolf, Polchinski, and Sully, poses a nightmare scenario. What happens to information at the edge of a black hole? According to Einstein's general relativity, crossing the event horizon should feel like floating through empty space, no drama, no sudden alerts. But quantum mechanics insists that information can't be destroyed, meaning whatever falls in must somehow be preserved on the horizon's surface like a cosmic hologram. Here's the catch: these two theories demand contradictory outcomes, creating an impossible rift in physics. Enter the firewall, a hypothetical wall of searing energy at the horizon that would vaporize anything attempting to cross. It's a brutal solution. Instead of peacefully entering the black hole, you'd collide with a deadly barrier of high-energy particles, preserving information by scattering it outward. But this creates another problem. Quantum mechanics forbids cloning information. It can't exist in two places at once. Yet the firewall scenario implies just that. Information both radiates away as Hawking radiation and continues its plunge into the black hole's depths. The universe, it seems, is breaking its own rules. One daring resolution, the multiverse. Picture information not as cloned but split, diverging into alternate realities at the moment of horizon crossing. In one universe, the data gets scrambled into Hawking radiation, escaping back into the cosmos. In another, it slips past the firewall unscathed, continuing its journey inward. This way, no single universe violates the no-cloning theorem. It's just that every possible outcome plays out somewhere. Think of it like a cosmic fork in the road. The original information doesn't duplicate. It branches, with each path leading to a distinct timeline where only one version of events unfolds. Support for this idea comes from quantum entanglement's bizarre properties. Particles entangled across the horizon could act as bridges, linking the interior and exterior of the black hole through correlations deeper than space itself. Some theories suggest these entangled partners exist in separate universes, their connections stretching across the multiverse's fabric. When radiation carries information away, it's not copying, it's trading places with its entangled counterpart in another reality. Critics argue this replaces one paradox with another, but proponents counter that it's the only way to reconcile quantum mechanics with relativity without invoking firewalls or information loss. After all, if the multiverse already accommodates infinite branching timelines, why not let it handle black hole paradoxes too? The AMP's dilemma doesn't just challenge our understanding of black holes. It forces us to confront the unsettling possibility that event horizons might be less like boundaries and more like portals, where every infalling bit of reality spawns a new universe with its own version of events. So the next time you hear about a black hole's darkness, remember, its true mystery might not lie in what it destroys, but in what it creates. Einstein once dismissed quantum entanglement as spooky action at a distance, but what if the spookiness runs deeper than he imagined? The ER=EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests something extraordinary. Wormholes and quantum entanglement might be two sides of the same cosmic coin. At first glance, they couldn't seem more different. Wormholes, those hypothetical tunnels through space-time, are the stuff of general relativity, while entangled particles are a quantum quirk. But dig into the math and an eerie connection emerges. Picture two particles entangled across the cosmos. Measure one, and the other instantly snaps into a corresponding state, as if they're sharing secrets faster than light. Now imagine those particles aren't just linked by some invisible thread, but by a microscopic wormhole, a shortcut through the fabric of reality itself. That's the heart of ER=EPR. The conjecture proposes that every entangled pair is physically connected by an Einstein-Rosen bridge, a wormhole so tiny it's woven into the quantum foam. It's as if the universe glues its distant parts together with hidden tunnels, making entanglement less like magic and more like plumbing. The implications are staggering. If true, it means quantum weirdness might be space-time's hidden architecture. Every time particles entangle, a wormhole forms, not in our familiar 3 dimensions, but in a higher dimensional bulk we can't perceive. These wormholes wouldn't let us send messages or spaceships, though. They'd be non-traversable, more like cosmic stitches holding the multiverse's seams together. But here's the twist. If you could somehow collect enough entangled particles, their microscopic wormholes might merge into a structure large enough to traverse, a backdoor to another universe. Support for this wild idea comes from black hole physics. When two black holes entangle, theories suggest a wormhole forms between them, bridging their interiors. Now scale that down to particles. The math shows striking parallels. The equations describing entangled particles mirror those governing wormholes. It's like finding the same blueprint for a skyscraper and a snowflake, a hint that nature might reuse its designs across scales. Critics argue this is speculative, but the conjecture solves thorny puzzles. For one, it bridges relativity and quantum mechanics, two frameworks that famously refuse to play nice. It also offers a fresh take on the black hole information paradox, suggesting data isn't lost inside black holes, it's teleported through wormholes to alternate universes. Even holography fits neatly. If our universe is a projection from a 2D surface, entanglement's wormholes could be the pixels connecting the code to the rendered image. Imagine the cosmos as a vast network of invisible tunnels, each a whisper between worlds. Every entangled particle, every quantum link, might be a handshake across dimensions, a hidden infrastructure we're only beginning to map. Whether ER=EPR holds up or not, it forces us to confront a breathtaking possibility. The universe's strangest phenomena might not be bugs in reality's code. They could be features meticulously woven into the multiverse's design. Quantum mechanics has a dirty little secret. Most of the weirdness gets erased before we ever notice it. That's the startling insight behind Wojciech's theory of quantum Darwinism. Imagine walking into a room where every possible arrangement of furniture exists simultaneously, chairs hovering near the ceiling, tables melted into the walls, a chandelier face-shifting through the floor. Yet somehow you always perceive the room as perfectly normal. That's essentially what happens in our universe. Out of countless quantum possibilities, only a select few survive long enough to imprint on reality. The rest vanish without a trace, like whispers drowned out by a chorus. Jacques' theory hinges on a process called environmental decoherence. When quantum systems interact with their surroundings, whether air molecules, light particles, or even cosmic background radiation, they don't just lose their fuzzy superposition states. They broadcast certain states more effectively than others, like a radio station overpowering weaker signals. These preferred states become reinforced through countless interactions, while others fade into obscurity. It's not that other possibilities cease to exist, they just become so drowned out by the noise of the universe that they're effectively invisible to observers like us. Think of it like evolution, but for quantum states. Just as natural selection favors traits that enhance survival, quantum Darwinism suggests the universe favors states that can withstand environmental scrutiny. A lone electron might briefly exist in multiple positions at once, but the moment it interacts with a detector, or even a stray photon, only the most fit state gets copied and amplified across the environment. The other possibilities don't vanish. They simply fail to replicate, like genetic dead ends in a cosmic ecosystem. This solves one of quantum mechanics' oldest paradoxes: why we perceive a stable, classical world despite its fundamentally probabilistic underpinnings. The answer: we're not seeing the quantum sausage being made. By the time reality reaches our senses, the messy quantum possibilities have been filtered through trillions of environmental interactions, leaving only the most robust states standing. It's as if the universe has an immune system that attacks quantum weirdness on sight, leaving behind a sanitized version of events we can comfortably call real. The multiverse connection lies in what happens to those discarded possibilities. In the many worlds interpretation, every quantum outcome spawns a new universe, but quantum Darwinism adds a twist. Not all branches are created equal. Some become reinforced and persistent, while others wither into obscurity, like ghost towns in the multiverse's sprawling metropolis. We don't perceive those fading branches not because they don't exist, but because they lack the staying power to leave an imprint on our world. Critics argue this still doesn't fully explain the collapse of quantum probabilities into definite outcomes, but supporters counter that it's the closest we've come to bridging the gap between quantum strangeness and classical intuition. Future experiments probing quantum systems in increasingly noisy environments could reveal whether certain states truly do outcompete others, or if we're missing a deeper layer of the puzzle. So the next time you marvel at the stability of the world around you, the way chairs stay solid beneath you or sunlight consistently warms your skin, remember, you're not seeing reality at its most fundamental level. You're seeing the version that won the cosmic popularity contest, broadcast loud enough to drown out the infinite whispers of what might have been. Have you ever sworn something happened a certain way, only to find out the world remembers it completely differently? Maybe you vividly recall the Berenstain Bears being spelled Berenstein, or Nelson Mandela dying in prison during the 1980s despite historical records showing he lived until 2013. These strange collective false memories have a name: the Mandela effect, and while psychologists explain them through quirks of human cognition, some daring theories suggest they might be something far wilder: glitches in the multiverse. Picture this: every time you make a decision, the universe splits. In one branch you turn left, in another you turn right. Most interpretations of quantum mechanics say these branches never interact. But what if they occasionally bleed into each other? Imagine shifting between parallel worlds where small details differ: a cereal box logo, a movie quote, even entire historical events. What feels like a false memory could actually be a faint echo from another timeline, a residual imprint left behind when realities momentarily overlap. The Mandela effect gets its name from the uncanny number of people who distinctly remember Nelson Mandela's death in prison, complete with news coverage and funeral scenes, none of which happened in our timeline. Then there's the Monopoly man's monocle. Ask anyone to describe him and many will insist he wore one, but pull out the board game and no monocle. Not now, not ever. Even pop culture isn't immune. Thousands swear Darth Vader's iconic line was, "Luke, I am your father." Nope, the actual quote, "No, I am your father." Skeptics rightly point to psychological explanations. Human memory is notoriously unreliable, prone to suggestion and distortion. Shared false memories often sprout from misheard phrases, misleading images, or cultural osmosis. The Berenstain spelling, for instance, likely stems from the prevalence of names ending in Stein, Einstein, Frankenstein, tricking our brains into autocorrecting the less familiar Stein. Social media amplifies these quirks, creating viral falsehoods that spread like digital folklore. But here's where it gets fun. Quantum physicists like Dr. Eric Weinstein have mused that if the multiverse exists, information transfer between worlds isn't entirely implausible. In the many worlds interpretation, branches of reality are closer than we think, separated by tiny quantum distances. Could certain minds, under specific conditions, tune in to echoes of nearby timelines? It's a fringe idea, sure, but not outright impossible. After all, if particles can exist in multiple states at once, why not memories? The truth probably lies somewhere in the middle. Most Mandela effects are textbook cognitive biases, but the sheer specificity of some accounts leaves room for playful speculation. Maybe these odd discrepancies are just the universe's way of keeping us on our toes, tiny reminders that reality might be more fluid than we assume. After all, if a single letter in a children's book can divide collective memory so deeply, what other facts might be up for debate? So the next time someone corrects you on how you remember a movie quote or a brand logo, don't just chalk it up to faulty memory. For a fleeting moment, let yourself wonder, did the world change or did I? From quantum particles that exist in multiple states at once to black holes that might spawn new universes, the evidence for parallel realities is more than science fiction, it's a frontier of modern physics. We've seen how Schrödinger's cat could be alive in one world and dead in another, how cosmic inflation might spawn endless bubble universes, and how anomalies like the cold spot in the sky could be bruises from a collision with another reality. The math behind string theory suggests a landscape of 10 to the power of 500 possible universes, while the holographic principle hints that everything we know might be a projection from a two-dimensional edge we can't even see. Even our own memories might not be safe, with the Mandela effect teasing the possibility that we're occasionally brushing against alternate timelines. Yet for all these tantalizing clues, mysteries remain. We still don't know why quantum mechanics behaves the way it does, or whether dark matter is truly matter from a mirrored dimension. False vacuum decay could rewrite the laws of physics overnight, and we wouldn't see it coming. The multiverse might be the answer to cosmology's biggest puzzles, or it might be the ultimate untestable idea, forever lingering just beyond the reach of experiment. So now it's your turn. Which of these theories grabs you the most? Is it the sheer cosmic sprawl of eternal inflation, where new universes bubble up endlessly? Or the spine-tingling thought that every quantum decision spawns a new version of you, living out paths you didn't take? Maybe it's the holographic universe, where reality is just a shadow play on the edge of existence. Drop your wildest speculations in the comments. Do you think we'll ever prove parallel universes exist, or will they stay forever in the realm of theory? And if you enjoyed this dive into the multiverse's most mind-bending ideas, don't forget to like and subscribe for more journeys to the edges of science. After all, in a cosmos this strange, the next big discovery might be just one quantum flicker away.